Hello, I'm Gordon Briggs, and I'll be presenting collaborative work done between the U.S. Naval Research Laboratory and the Human-Robot Interaction Laboratory at Tufts University. Our talk is entitled, "What Are You Looking At? Integrating a Computational Model of Attention with a Cognitive Robotic Architecture." In our daily lives, we often shift our attention between both stimuli in the external world and internal mental processes, and gaze direction is a key signal of this attentional focus. Successful social interaction often depends on making correct inferences based off of gaze. For instance, consider the example of an agent, in this case a PR2 robot, asking an interaction partner, "Should I pick up the blue light bulb?" Note that depending on your perspective, you might see multiple blue light bulbs, making this an underdetermined reference. But the gaze direction of the robot provides an additional disambiguating cue to help you infer which item the robot is referring to. The aim of this work described in this talk is to help enable robots to produce more natural and human-like gaze behaviors to improve human-robot interactions across a wide variety of scenarios, including ones like these. Because the importance of gaze in facilitating social interaction has long been recognized, a variety of prior computational approaches to generating gaze behavior in HRI contexts have been developed. In a survey written by Admani and Scazzolati, 3 categories of prior approaches were identified, including data-driven, heuristic, and biologically inspired approaches. Data-driven and heuristic approaches are trained or tailored, respectively, for specific tasks and specific robotic platforms. In contrast, biologically inspired approaches use models of human perception or cognition as a basis for generating gaze behaviors. While these model-driven approaches tend to be more generalizable, they still suffer from some shortcomings. Namely, that the models that they are based on are either fine-grained models of visual attention or broad models of human cognition that don't necessarily have dedicated attentional mechanisms. Here we propose a novel model-driven approach that attempts to bridge both bottom-up perceptual and top-down cognitive processes. To do this, we developed an integration between 2 pre-existing architectures: the direct cognitive robotic architecture, primarily developed by Tufts University, and the Arcadia modeling framework, developed at NRL. The direct architecture provides a flexible basis to interface with and control a variety of robotic platforms, as well as other capabilities such as natural language communication and 3D visual processing faculties. Arcadia provides a cognitively inspired framework that has attention as a central architectural mechanism, which can be used to guide a robot's gaze direction. The aim of the direct Arcadia integration is to provide a task and platform agnostic means to drive robot gaze behavior, factoring in both bottom-up perceptual and top-down cognitive considerations. For additional details on the integration, we refer you to our short paper. As Arcadia, unlike Direct, is relatively unknown in the HRI community, we wanted to take a moment to discuss it further. Arcadia operates in discrete cognitive cycles. On each cycle, a series of components produce informational elements based on input from sensors or the previous cycle's information buffer. Additionally, Arcadia uses an intentional strategy to select a single informational element to be the focus of attention, which is broadcast to all of the components. Components may or may not engage in information processing differently depending on the focus of attention, allowing Arcadia to model both attention-dependent and attention-independent perceptual and cognitive processes. For instance, Arcadia has been used to build fine-grained models of a variety of human psychological phenomena, including perceptual tasks such as multiple object tracking, and tasks that begin to bridge both perception and cognition, such as number perception and causal judgment. Here we present a proof of concept demo showing the Arcadia direct integration in action. In this demo, multiple objects are in front of a PR2 robot. Direct recognizes these and forwards 3D object information to Arcadia. Arcadia's attentional strategy in this demo is configured to perform a simple inhibition of return behavior, deprioritizing objects that have already been fixated on. Thus, an active shifting of robot gaze between objects emerges from the simple attentional strategy. And here you can see a new object is introduced. And because it hasn't been fixated on before, it's prioritized. And then the robot returns to just randomly shifting its behavior or shifting its gaze between objects. While the behavior demonstrated in the video is fairly simple, the range of behaviors enabled by this integration is wide. We're taking the initial integration demonstrated in the video and extending it in various directions, building more complex models using more information transfer between Direct and Arcadia, as well as more complex Arcadia attentional strategies. One example of such an extension is using the integration to generate gaze behaviors during task-based dialogue interactions. For instance, during an interactive object learning task, gaze can be used as a cue to indicate that the robot is learning the correct label for the correct object. This work is currently under review. Other areas include using the integration to enable active perception, that is the use of gaze shifts to enable proactive information gathering, as well as cross-modality attentional cueing. Our section at NRL has developed capacities to use auditory cues to capture visual attention. It'd be straightforward to use this integration to demonstrate this in an HRI context. Finally, in our short paper, we present one possible way of integrating Dirac and Arcadia. Other possible integration configurations could be explored, including using multiple instances of Arcadia to have dedicated foci of attention for specific robot modalities. To wrap up, we wanted to acknowledge that this work was supported and made possible by an award from the Office of Naval Research. We'd like to thank you for your attention, and we look forward to your feedback and questions.